What if you could understand language, like directly from the electrical hum inside someone's brain?
Uh-huh.
Not words they speak, not text they type, but the actual thought captured just from electrical signals.
It sounds like science fiction, doesn't it?
Totally. But that's the incredible frontier we're diving into today.
And it's moving surprisingly fast from fiction to fact. We've got this stack of sources, research papers, articles, notes, all exploring this edge. Specifically, how AI models are learning to pick out language from, well, the really messy signals you get from EEG, electroencephalogram.
Right. So our mission here is to kind of cut through that complexity. We want to unpack the main challenge, look at the clever ways AI is being used, maybe celebrate some breakthroughs.
Yeah, and see where it's all heading.
Exactly. Think of this as, your shortcut to getting a handle on a field that could genuinely change things. We're aiming for those aha moments for you without getting totally lost in the weeds.
Sounds good.
Yeah.
Where should we start?
Okay, so basics first. This EEG speech decoding. What exactly are we trying to do?
Fundamentally, you're using AI, right, to try and extract linguistic information, basically. What words or thoughts someone is processing directly from those electrical patterns measured on the scalp,
From the EEG.
from the EEG signals, yeah. It's really about trying to decipher the brain's electrical language.
And that sounds, well, incredibly hard because
Wow.
why? What's the big hurdle?
It's just so noisy. The signals are notoriously noisy. Imagine trying to hear a single whisper in the really loud, crowded room.
Okay.
Brain signals linked to language are subtle, and they get easily drowned out by all the other electrical activity, muscle twitches, eye blinks, even just electrical noise in the environment.
Ah, okay. So that's the signal to noise ratio problem,
Yeah.
SNR.
That's the one, low SNR. It's the main mountain everyone's trying to climb in this field.
So everything else your body does electrically is just static, basically, making it hard to find the signal you actually want.
Precisely. It's a massive challenge. And then there's another layer.
Hmm.
Everyone's brain is a bit different.
Right.
So an AI model trained to decode signals from me might not work very well for you without, specific adjustments, calibration.
Uh-huh. So generalizing these models across different people is also really tricky.
A real hurdle, yeah.
Okay, so the signal's weak, it's buried in noise, and it's different for everyone. How on earth does AI even start to tackle this?
Well, that's where all the cleverness comes in. Researchers are basically using a whole toolbox of AI and machine learning methods.
Okay.
Think of them as different kinds of pattern detectors, each good at finding slightly different things in those complex electrical waves that might, just might, relate to language.
What kind of tools are we talking about? Are these familiar AI names?
Some might be.
Yeah.
You see deep learning models like convolutional neural networks, CNNs. People often use those for images, but here they're adapted to find spatial patterns, like across the different electrode locations on the scalp.
Ah, okay. Patterns across the head.
Yeah. And then there are recurrent neural networks, RNNs. They're really good at handling sequences of data over time.
Which EEG data is, right. It changes moment to moment.
Exactly. So RNNs help capture that temporal dynamic.
Yeah.
But increasingly, the big player getting a lot of buzz is the transformer architecture.
Okay, transformers, like the things behind ChatGPT and all that.
The very same. Those models are incredibly powerful at understanding context and generating sequences. And it turns out that ability translates surprisingly well to decoding these complex sequential brain signals, too.
Huh. So it's not just about spotting one word, it's about the flow, maybe predicting what comes next.
You got it. And that leads into another exciting area mentioned in the sources, the integration of generative AI.
Generative AI, like GANs or those LLMs you mentioned.
Yeah, exactly. Models like generative adversarial networks and those big transformer-based language models, they're helping move the field beyond just simple classification. This signal pattern means hello,
Yeah.
towards actually generating language output.
Whoa, okay. But how do these models even look at that raw EEG data?
Yeah.
It's just squiggly lines, right? How do they make sense of it?
No, they don't look at the raw squiggles directly. There's a critical step, or really steps, before the AI even sees the data. It's called pre-processing.
Cleaning it up?
Basically, yeah. Using sophisticated filtering techniques to try and strip out as much of that noise and artifact the eye blinks, muscle tension as possible.
Okay.
And then there's feature extraction. The AI isn't usually looking at raw voltage values. It's looking at derived features from the signal.
Features like what?
Things like the power in specific frequency bands, alpha waves, beta waves, that sort of thing. Or maybe how synchronized the activity is between different brain areas or specific patterns that appear over time. The AI learns which combinations of these features are the most predictive of the intended word or thought.
So clean the data, find the important electrical fingerprints, and then let the AI learn the connections.
That's a great way to put it. And yeah, getting that pre-processing and feature extraction right is absolutely crucial, especially with that low signal-to-noise problem.
Okay, now here's something that seems really key in the research, maybe a bit counterintuitive. Imagined speech. What's that about?
Right. Imagine speech, sometimes called covert speech. It's basically thinking the words, forming the sentence in your head, without actually moving your mouth or vocal cords to say aloud,
Just thinking it.
just thinking it. You activate the brain areas involved in planning speech, but you don't execute the motor commands.
And why is that so important for decoding?
Because the muscle activity involved in actually speaking creates a huge amount of electrical noise that contaminates the EEG signal. It's really strong compared to the underlying brain signal.
Ah, so by focusing on imagined speech, you get rid of a major noise source.
Exactly. You bypass the muscle artifacts, allowing the AI to focus more clearly on the neural signals related purely to the language planning itself. This is obviously super relevant for assistive communication.
Right, for people who physically can't speak, accessing their imagined speech seems like the most direct route.
Precisely. And this is where those newer AI models, especially the generative ones, are making a massive difference. They're enabling a shift beyond just identifying single words towards syncta, but towards generating continuous output.
Continuous output, what do you mean by that? Not just one word at a time.
Yeah, exactly. Instead of the AI, say, picking the most likely word from a predefined list based on the signal, some of these newer models can take the ongoing brain activity and generate a whole flowing sequence of text, or potentially even synthesize speech that corresponds to the complete thought or sentence the person is imagining.
Wow. So much more like natural language.
Much more natural, much more expressive. It's a huge leap compared to just selecting options. It gets closer to capturing the actual flow of thought.
That really does feel like a game changer. Now, we often hear about other brain interfaces too, right? Like implants. How does EEG compare?
Good question. The sources definitely touch on other BCI, brain-computer interface methods. You have invasive techniques like ECOG electrocorticography. That's where they place electrodes directly on the brain surface.
Ooh, more direct signal, I
Yes,
guess.
definitely. You get much cleaner, stronger signals because you're right at the source, bypassing the skull and scalp. And that often leads to higher decoding accuracy.
Ah, surgery.
But surgery, yeah. Significant risks, not something you do lightly. There are also other non-invasive methods like MEG, magnetoencephalography, or FNIS, functional near-infrared spectroscopy. They measure different things, magnetic fields or blood flow changes.
Okay, so where does EEG fit in that landscape? Why focus on it if it's so noisy?
It really comes down to practicality and accessibility. Despite the noise challenge, EEG is non-invasive, it's relatively portable, and it's much less expensive than something like a MEG machine.
So it's the one with the best shot at being widely used, maybe outside a lab someday.
That's the hope, and that's why there's so much research pouring into improving it, tackling that noise, refining the AI. It's all driven by EEG's practical advantages.
Makes sense. And all this AI development, it must need tons of data, right?
Oh, absolutely.
Yeah.
Training these complex models takes a lot of examples. Thankfully, the field is pretty good about sharing. There are publicly available EEG data sets specifically created for this kind of speech decoding research. You can find them on platforms like OpenNeuro, Kaggle, Zenodo.
So researchers can build on each other's work.
Exactly. Those shared data sets are really crucial for pushing the whole field forward.
Okay, let's zoom out a bit. The so what question. Why should this tech matter to you listening right now? What's the real impact?
I think the most immediate and honestly the most profound impact is for assistive communication.
Right.
For people who've lost the ability to speak, maybe due to ALS, stroke, severe injury, this technology offers a potential pathway back, a way to communicate their thoughts, their needs, their personality again,
Giving a voice back.
giving a voice back, essentially. It could restore connection, autonomy. It's potentially life-changing. And BCIs, more broadly, have huge potential in healthcare and beyond.
That's incredibly powerful. But,
And-
okay, tapping directly into brain signals. That immediately brings up some big questions, right? About privacy, about what's going on inside our heads.
It absolutely does, and it should. Decoding brain activity raises really significant ethical considerations. If technology can potentially access someone's internal monologue or even unspoken intentions, how do we protect that?
Yeah.
There's a really important growing focus now on things like neurodata consent frameworks, Basically, designing systems where individuals have very clear understanding and control over how their brain data is accessed, how it's used, who sees it.
Neurodata consent. That sounds like a term we're all going to need to get used to.
I think so. It's
Ah,
part of a wider conversation about neural rights.
right.
Yeah, the idea that maybe we need new kinds of human rights specifically focused on protecting mental privacy, cognitive liberty, as these neurotechnologies become more powerful. It's critical that we're having these ethical discussions now as the tech develops, not after the fact.
Definitely sounds crucial. So looking down the road then, what's next for this field? What improvements are on the horizon?
Well, you can expect progress on a few fronts. Hardware-wise, people are working hard on better EEG sensors, things like dry electrodes.
Dry ones, meaning no conductive gel.
Exactly. Much less messy, potentially more comfortable to wear for longer periods, easier to put on. That could make EEG headsets much more practical for use outside a lab, maybe even at home.
Okay, that's a big step for usability.
Huge. And alongside that, you'll see continued refinement of the signal processing, getting even better at filtering
Mm.
noise, pulling out those key features, and of course, the AI algorithms themselves will keep getting smarter. Probably more sophisticated generative models, better training techniques, all aimed at boosting accuracy and making the decoded output sound or read more naturally.
So it feels like we're still really in the early days of what this could ultimately do.
Oh, absolutely. It's a very active research area. There are roadmaps being discussed, lots of ongoing work. The challenges, especially that noise problem, are still really significant, but the progress is undeniable,
Oh.
and it's driven by that incredible potential for impact.
Wow. Okay. So we've gone from these faint, noisy electrical brain signals, explored how really sophisticated AI from, deep learning basics to advanced generative models is learning to pull out meaning, especially imagined speech.
Yeah, opening up these amazing possibilities for communication assistance.
Right. But we've also acknowledged those big technical hurdles that remain and touched on these really vital ethical questions about neurodata and privacy that are starting to surface.
It's a complex picture, definitely, but like you said, a hopeful one too.
It really is. And maybe it leaves you, the listener, with something like this to chew on. If we get better and better at decoding our internal imagined speech, how might that actually change our basic idea of what communication is? Does this kind of tech start to blur the line between our private thoughts and what we express externally? And if it does, what really fascinating new questions does that raise for all of us down the line?